Hi, today we're going to be going over the Java solution for Leetcode 704, binary search. Binary search is a fundamental algorithm in computer science, and basically we use it to search for elements in a sorted array. And the advantage is that it's really, really fast. So this problem right here, this isn't really sort of like a thinking problem. You don't have to think about anything. It's just to help you implement binary search either for the first time or to get a bit more practice with it. So the problem goes something like this. Given an array of integer nums, which is sorted in ascending order. So the key here is that it is sorted. Binary search only works in sorted arrays. They can be sorted in descending or ascending order. It doesn't matter. And an integer target. Write a function to search target in nums. If target exists, return its index. Otherwise, return -1. So to go through this example right here in this integer array, and a target of 9. So we have to look through this integer array and find 9, and we see it does exist right here, and we're just going to return its index, which is 4. So if you didn't know about binary search, your initial idea might to be, loop through the whole array and then see if it appears. And if it does, then that's great. Then we can just return the index, which in this case would be I. And if it doesn't, then we know that it doesn't appear at all in the whole array, so then we could just return -1. So here, this is fine. It's just that the problem is we aren't using the advantage that we have, that it is a sorted array. This would be O of n runtime complexity, so it is linear, while binary search is O of log n runtime complexity, which is much faster. So running binary search in this, the algorithm goes something like this. We're going to set up two boundaries. I'll set up an I is equal to 0 and an int j, which is going to equal nums.length -1. And basically, our whole idea is that these are our boundaries right now. So that is I, that is j. We're going to calculate the middle. So in this case, it would be 3. And we're going to compare to see, number one, does the middle, is this number equal to the target? If it is, then we could just return its index. In this case, it's not. Then we'll compare, is this value less than or greater than? Since it is less than, we can use the idea that it is sorted to basically eliminate this entire left half. We don't have to search in this left half at all, because all of these elements will be less than our target no matter what. So then we could instead shorten down our basically view. So instead of I being here and then j being here, where we will calculate the middle with 3, our I now will be 5 and our j stays the same. And so now we'll calculate the middle between these two, which would be 9. And again, we'll compare. We see that 9 is the target, and so we could just return that. But basically, we're going to be shortening it down, basically halving it each time until we narrow it down to one element, and that is going to be our target. And if it doesn't exist, then we know it doesn't exist at all in the whole integer array, so then we could just return -1. So the way we implement it is that we'll set up a while loop while I is less than equal to j. So this is basically telling us that we're going to shorten down these boundaries, basically halving them each time. And, there's going to be a point where we're going to narrow it down to like one element. And if that does not equal our target, then we're going to narrow it down even further, basically go into opposite directions. And that's going to end our while loop, basically telling us, hey, we've already checked through the whole thing. So the main implementation is that we're going to create another variable, a middle. So this middle is going to be the middle between I and j. So that's just going to be I plus j divided by 2. However, in Java, and I'm pretty sure many other programming languages, this can sometimes result in integer overflow. So that's why instead we do I plus j minus I divided by 2, and you can test this out for yourself. This is saying the exact same thing as just finding the middle. So now we could go through our if statements. So if nums of mid is equal to the target, then great, we've already found the index, and we know it exists, so we could just return the index, which is the mid. Else, if nums of mid is greater than the target, then we know that this middle index is highball. It is overestimating where the target might be. So we gotta cut down the upper boundary. So we can set j is equal to mid minus 1. Else, in this case, it is a low ball. The nums of mid is less than the target, in which case we lowball this, so we could bump up the lower boundary to cut off in that half. So I can be equal to mid plus 1. So basically running it through this example, what this is happening is that we'll start out with I being here and j being here, and then our middle will be 3. We go through it, we see that is not equal to the middle, and we see that it is not equal to the target, as well as, it's not greater than the target. In fact, it's less than the target. So we'll execute this. I will be equal to mid plus 1. So instead of I being negative 1 right here, our new I, our lower boundary, will be a 5. Or will be this index 3, or this element 5, and our j is still at 12. So now we've cut down these 3 elements, we've eliminated them, and now we can just compare this as our view. We know our target will reside in this, or at least it should. And then we calculate the middle, that would be 9, we see that it is, and then we could just return the mid. So if we go through this and our loop breaks without returning the middle, then we know it doesn't exist at all, so we could just return negative 1. So let's see if this works. Great. And so, yeah, that's the great thing about binary search. It's super fast, it's super efficient, and basically it's just using the idea that, the whole array is sorted to use that for our advantage.